next to the 676 by 8. And what will be that number? That will be 91 multiplied by which value? The rotated kernel, 0, plus 112 times minus 1, plus 1 times 87, plus 1 times 70, plus 1 times 40, plus 0 times 90, plus 3 times 82, plus 1 times 65, plus, 2 times 65, plus 1 times 33, whole thing divided by 8.
494, that is divided by 8 would be 61.75.
61.75. So basically our result of the convolution, as you can see, is 84.5, and what did you say?
61.75.
1.75, right? Same way we'll produce an answer in the next one. Slide the window to one more, right? After we are done with the first row, we'll start sliding the window down. Okay, so what you will see is, other than the first row and the first column, there will be nothing in the first row, first column, and the last row, last column. But there will be numbers everywhere else. I mean, not zero, some number, whatever that number is. Okay? So some numbers will be produced other than that. And the reason is because with the 3 by 3 kernel, the first position produces the answer in this spot. Okay. So if we really wanted to put some numbers in the first row, first column, okay, you could put the kernel to the negative side and see, meaning treat as if these were all zeros. That would be one option. Or think of this like a folded thing. Whatever was the last column was, put that over here, then move the kernel to the left, so this way you can fill these out. But typically in most situations, we don't worry about if we had 1,000 rows, 1,000 columns, if one of the rows, one of the columns is missing data, meaning it has zeros, no big deal, okay? So to summarize, if we are given a kernel, so in this example, it was a 3 by 3 kernel. If we are given a kernel, then how do we do the convolution with a given image? We rotate it by how many degrees? 180, which is basically 2 rotations of 90 degrees. Once the kernel has been rotated, then it's very easy. Put it in the first spot, multiply and add, slide, 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 the kernel, slide, 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 and keep multiplying, adding until we produce the result, right? So here's the interesting part. Depending upon what we put in these, what numbers we put in this kernel, it will produce a certain kind of effect after the convolution. So if we pick it carefully, it will remove the noise from the image. If we pick it in a certain way, as I will show you, it will do edge enhancement. If we put it in a certain way, it will do sharpening of the image. Or it will create the effect as if you're looking at this image from a far, far away. So it will appear blurry, but as if it's being viewed from a very long distance. Okay, so anyway, so our next goal now is to how do we come up with a kernel? Okay, so let me give you.
Does that mean that it will reduce the size of the image after convolution?
Yeah, so we lose the first row, first column, like I said, unless you do a zero padding on each side, then you won't lose it. Or unless you treat it as if this is like wrapped around, so that you duplicate the last column in the first position, then you will not lose it. Okay. So anyway, so the big question, like I said, is how do we kernel values. Okay, so let me show you some of these. You'll be able to now answer me right away. Okay, suppose goal is to remove noise. High frequency noise. Okay, see, when I was giving you the stock market example, these daily changes, you know, up and down, those are high frequency. Frequency is basically a change. Okay, if I gave you a signal like this, okay, the change is occurring very slowly, as opposed to if I gave you a signal that goes like this, changes are occurring relatively quickly. So one way to filter will be to remove these high frequencies so that it results in a smooth image. Okay, if you can keep reminding yourself, anytime things change quickly, a lot of frequencies are involved. Okay, remember I said in the time domain world, if I take a look at the impulse function, delta t, okay, so it was 0, 0, 0 over here, and then what happened to its amplitude once we came over here? Infinity. So is that a very quick change?
Yes.
Anytime we change something very quickly in the time domain, it causes infinite frequencies. Okay, so if we have time, we'll go over that concept. Sometimes we need it even in computer vision, and that's called a Fourier transform. So I'll give you the intuitive idea for right now. So the job of the Fourier transform is to take a look at the frequency component of a signal. Okay, for example, let's say I gave you a 60 hertz sine wave. Okay, if I did the Fourier transform of it, what we will do is we'll produce one impulse at 60, meaning in the frequency world, there's only one frequency present in this wave, and that occurs at 60. Okay, if I gave you a signal which looks like something like this, pretend it's the sum of 30 hertz wave, 60 hertz wave, 100 hertz wave. We added them, and let's pretend it came out to be like this, right? If we do the Fourier transform of it, what will it show us? There will be one pulse at 30, one pulse at 60, and one pulse at 100. So basically, Fourier transform tells us what is the frequency components of a signal. Okay, so now let me ask you this. If this is in the time domain, it changes extremely rapidly. Okay, if I do the Fourier transform of delta of t, can you tell me what would it look like in the frequency domain? Will it have one frequency, or will it have a lot of frequencies? Lot of frequencies, right? Infinite frequencies. So it will be basically a flat line, meaning all frequencies are present. Okay. So anytime things change rapidly, okay, so suppose I gave you a signal like this. It goes and then becomes high immediately. At that point in time, so if this is in the time domain, in the frequency domain, what will happen? It will cause a few frequencies or many, many frequencies. Excuse me. It will cause many, many frequencies, right? So, okay, so anyway, coming back to our understanding of how do we come up with a convolution filter, okay? If our goal was, let's say, to remove a high frequency noise, right? Then what kind of filter we want? So let me write it for you. Okay, so goal is come up with a kernel to remove high frequency noise. Okay. So if we are removing high frequencies, what kind of filter are we looking for? A high pass filter, low pass filter? See, that means we want to block the high frequencies, right? No, low pass filter, because meaning we want to pass all the, see, these are low frequencies, these are high frequency. We want to block the high frequencies because we want to remove those, right? So this is called the low pass filter. Okay, so this is our goal in the frequency domain. Okay, as I mentioned to you, what is the easiest way to accomplish a low pass filter? The average filter, right? The moving average, as we discussed. Okay, so one easy way to accomplish low pass filter is do averaging. So in other words, if I added all these pixels, right? Like these 95, 91, 112, 83, 70, 40, 91, 82, 65, and just replaced it by the average in this spot, it will remove the noise, the high frequency noise, right? So now my question to you is, what will be the value of that kernel?
1 over 1?
No, 1 minus 1.
In terms of dimensions or the actual value?
Actual values.
1 over 1.
I want to accomplish the averaging of all the numbers.
All ones? All ones divided by 9?
All ones divided by 9. See how easy it is? So this is basically a very, very easy noise removal filter. Okay, it does a low pass filtering. Sometimes we use 3x3 kernels. What if somebody said, "Oh, we want it to be a little more accurate. Let's use a 5x5 kernel." So if I ask you to give me a 5x5 kernel that will do the averaging or the noise removal or the low pass, what will be that
All
kernel?
1 divided by 25.
All ones. Divided by 25. Okay, perfect. So now, just like I mentioned to you in the signals work, the delta of t is a very special function. Okay, if I do the convolution of delta t with any signal, so if I have f of t convolution with delta t, what do I get? The same signal. Okay. I also mentioned that convolution in the time domain is what? Multiplication in the frequency domain. Okay, so now let's pretend this f of t happens to be some, let me make it some x of t rather than, because f is frequency, so that I don't want you to get confused over here. So x of t. So typically we use lowercase letters for the time domain, for the pixel domain, and uppercase letters for the frequency domain, right? So now suppose I did a Fourier transform of x of t, okay, and it came out to be x of f. Okay, it doesn't matter what it looks like. It will tell us the frequency component of this, right? Then I did the Fourier transform of delta of t. It will be 1 as we discussed. So this is guaranteed to be 1. Okay, now the convolution becomes what in the frequency?
Multiplication.
Multiplication. So what is x of f multiplied by 1?
The same to x of f.
X of f. Okay, now as to understand it a little bit more intuitively, suppose this was an audio signal. X of t was audio. right? As you guys know, our human ears can hear up to 20 kilohertz. So if I did this Fourier transform and looked at the frequency spectrum, it will have pretty much everything up to 20 kilohertz, but very few things afterwards. Okay, delta of t, as you can see, is all. If I multiply the two, what will I get?
The same thing.
The same signal, so it doesn't do anything. Okay, now let me ask you, what if I wanted, so my question is, just like delta of t, if we do a convolution with any signal, it doesn't do anything, gives us the original. The time domain is equivalent to the pixel domain for images. So what is the equivalent of delta t? So give me a delta n kernel, so that if I do the convolution with this one, it doesn't do anything. It gives me the original image.
Oh. All ones?
No, minus center.
Yeah, that should be 0.
No, yes, you got it. It's one, because see, we don't want the 70 value to change.
Oh, yeah, but
Okay, so do you guys agree this should be 0, 0, 0, 0, 1, 0, 0, 0, 0. Everybody agrees?
the 9 should be
9 should be removed. There's no need for it. So this is what we call identity kernel in image processing. So two kernels you guys already know. One is the averaging kernel, which is all ones divided by 9. And what is the identity kernel, which doesn't do anything, right? Makes perfect sense. Okay. Now, sometimes people get confused. Suppose I gave you a matrix. 1, 2, 3, 1, 5, 9, 6, 8, 4. Okay, I want to multiply it with another matrix such that I get the same data back. So forget images, now we are talking about matrices.
more the same data.
So if I multiply it with a certain matrix,
You can get the exact thing back.
I want the exact original back.
If the determinant of that matrix is 0, then like 1 and minus 1 all.
So my question is, will this work?
No.
1 0 0 0 1 0 0 1.
Yes, so remember in the matrix world, what is the identity matrix?
Diagonal is all.
Diagonals are all 1.
Diagonals are all ones. And you can easily verify it if you remember we do row by column multiplication, row by column, you'll get the original back. Okay, so what I'm trying to say is we'll still be writing this as capital I. Sometimes people forget that they think they're dealing with matrices and not images. So instead of using this as the identity, they start using this, which will totally destroy the image. Okay, so anyway, for image processing, identity kernel is where we have one in the middle, everything else is here. Okay, everybody good so far?
Professor, how do we know what size of kernel we should use? 2 by 2, 3 by 3, 5 by 5?
The higher the kernel, the more accurate it will reproduce, but the computation cost goes higher. For example, let's say we were using 3 by 3 kernel, right? How many multiplications and additions we have to use? For each value that we produce on the output. 9, right? But if I use a 5 by 5 kernel, 25 multiplications and then one big addition. Okay. So if you're processing real-time video as an example, and you started to use a 13 by 13 kernel saying, oh, you'll do a fantastic job, then you'll process one frame, there will be a 5-second delay with the second frame. So anytime real-time or time is a constraint, we use a smaller filter. But if it's a still image, let's say there's some security application, you wanted to, there's some image that was taken and you wanted to enhance it in a certain way, then by all means use as big of a filters which will do the best job as it can. Okay, so now coming back to our two filters that, yes.
Could you clarify again how the convolution filter with just the one, convolution kernel with just the one in the middle affects the image versus?
It doesn't affect it because see, take a look over here.
So that was the purpose, it doesn't change anything?
It doesn't change, and that's the purpose of the identity operation. Once you apply an identity operation to any other data, it should not change the data.
Well, versus the all ones divided by 9.
That changes the data
Changes
because
the
then
data
it
completely.
gets replaced by an average of all the surrounding values. Yes.
And by the first row and the first column, last row, last column is still removed, right?
Yes, still is an
No
issue.
effect of the image.
Yeah. So again, like I said, if you wanted to incorporate the last row, last column, first row, first column, either do a zero padding in the original image, make it 1 pixel bigger on each side, or you treat it, or you duplicate this row, the first row, or you go to the last row and place it over here. So you'll see as we go to more advanced applications, sometimes we don't want the output image to get reduced. So then we'll do these padding techniques to make sure that it still stays the same size. But as is, let's say I gave you a 100 by 100 image. Okay, and we applied a 3 by 3 convolution to it. What will be my correct resulting image? 98 by 98. Because you lose one row, one column, bottom, top, left, and right. Okay? But if you were doing 5 by 5 convolution, 96 by 96, right? But with the padding, we can then keep it 100 by 100, as we'll see later on. Okay, so coming back to our understanding of convolution and creating kernels of ourselves. So the two kernels that we have discussed so far is the identity kernel, which doesn't do anything. And that is 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, and we've also discussed the moving average, or let me just call it average kernel. Okay, which accomplishes what kind of filtering? Low pass filtering, right? For a 3 by 3, this will come out to be divided by 9. Everybody's good so far, right? Okay, so now let's take a look at slightly more useful type of filters. Okay, I mean average is useful, identity is more for a theoretical interest, but it will help us actually create other type of kernels, as I will show you. Okay, so if we take a look at the low pass filter, right? Remember this was in the pixel domain. Okay, sometimes what we do is, just like if somebody gave you a signal in the time domain, we'll try to visualize it in the frequency domain to see, what's the frequency content of it. So very similarly, if I try to visualize this particular filter in the frequency domain, what would it look like if this is frequency? Okay, this is the amplitude. Okay, will it look like this?
No.
Will it look like this?
Yeah.
Yeah, it's a low pass filter, right? So obviously it will look like. So how good of a low pass filter it is? Okay, that depends how sharp this edge is. Okay, so if, for example, somebody may give you a filter like this. Okay, it is doing some kind of a low pass, but you know, it's passing a lot of frequencies over here. Even though they are being attenuated, it's still passing. A better filter obviously would be, like I said, which behaves more like this. Okay. Even though in the ideal world we would like to be perfectly vertical, but in the practical world, no matter what we do, there will be some kind of curve to it. Okay. So if you can take my word for it right now, if I did the Fourier transform, 2D Fourier transform, and try to visualize it, it will look something like this. And then gradually goes to 0. So this is basically the kernel filter's frequency behavior. Okay. So sometimes what we want is sometimes we want a better low pass filter. Okay. With the frequency response. You know, this was for the low pass case. We may like it to be something like this. Okay. Let me see if you guys can help me out over here. In the frequency domain, there's a mirror effect. Okay, meaning there's also negative frequencies, so this looks like this. Okay. Same way if I did the mirror of this, it will look something like this. You guys have seen this type of signal before. What is this signal? Yeah, Gaussian, exactly. Okay, see, a Gaussian looks like this. Centered around 0, right? This is the standard deviation, for example, where about 67% of the data lies, right? Okay, so a Gaussian function okay, if we take a look at the equation of the Gaussian function, so for example, it will be 1 over 2 pi sigma square root e to the x minus mu. Mu is the mean square over 2 sigma square. So if I remember correctly, this is the formula for the Gaussian distribution. Okay. And so sigma is the standard deviation. So if sigma is small, what kind of curve will it produce? More like this, right?
Yeah.
If the standard deviation is wide, what kind of curve it will produce? More like this. So this is, suppose instead of x I say g of t in the time domain. If in the time domain it looks like this, remember our goal is to create better filters, right? Filter whose response in the frequency domain looks like this. Okay, that's our goal. So this is our goal. Okay, so if we are given a time domain Gaussian function, the question is, what does it look like in the frequency domain? Okay, here's the neat thing about it. Okay. If I was teaching you signal processing, I'll go through the whole math and show you exactly. But for right now, if you can take my word for it, that the Fourier transform of a Gaussian function is Gaussian itself. So that's the beauty of the Gaussian function. Okay, so if I gave you, let's pick this as an example. So this is pretend in the time domain. What will it look like in the frequency domain? Same. So in the frequency domain, it will also be me try to make it as close as I can to this one. Still not close. Okay, so this is basically, the difference is now this is frequency. Okay, and you can see with the moving average filter, we have these little ripples being created, which will still pass some high frequencies. The Gaussian will tend to block those frequencies. Okay. So now the question is, what is the Gaussian kernel? Okay. If I gave you, remember this is now two-dimensional, right? Two-dimensional information, right? If I gave you some numbers, okay, what would you expect the center number to be?
Higher.
Higher. You know, just like, see, take a look, in the middle is the highest, okay? But we want to know the exact value. See, the exact value here depends on what?
The outside.
The adjacent values.
It depends on, okay, first, I'll give you a two-dimensional version of the Gaussian function in a second. This was a one-dimensional function, right? See, the shape of this depends on which of the parameters over here.
Sigma.
Sigma. Does the mu also affect?
Yeah. The place.
No, because when I center it on the 0, that means mu is 0, so I can eliminate the mu essentially, right? Okay, so the two-dimensional version of the Gaussian function. Okay, so let's go to g of xy is 1 over 2 pi sigma squared. Okay, in reality there will be mu sigma x, sigma y, but I'm assuming
Yeah, the 0.
assuming 0 mean and symmetry around origin. And x and y. Okay, meaning that it's the same sigma for in the x direction, same sigma in the y direction. So then this becomes e to the x. X minus mu squared. Yeah, x minus mu. See, typically it will be x minus mu squared, y minus mu squared divided by 2 sigma squared. So if I do, yeah, I think it would come out to be x squared plus y squared over 2 sigma squared. Okay, I'll double check that, but I think this is the, based on my memory, this is the equation for the two-dimensional Gaussian. Okay, so now the question is, what is the exact kernel? Okay, obviously based on the sigma we pick, it will be a different value. So the way we come up with the kernel is, so 3 by 3, 2D.